Okay, in this segment, I'm going to show you the basics of using POSIX threads. And obviously, it can be a very deep topic, and multi-threaded programming in general is very complex. But there's a pretty small subset of it that you can use to go pretty far with multi-core programming. And that's because a lot of parallel programming is applied toward problems that have data parallelism. What do I mean by data parallelism? Well, you have a large array, you have some big buffer of data, and you want to perform the same operation on every element of the data. Okay, so it could be like doing a dot product, or it could be adding two vectors, or it could be doing matrix multiplication, or it could be doing some discrete version of a differential equation, which looks like some stencil-based numerical operation. Whatever the case might be, oftentimes the things you want to speed up are floating point intensive and contain a lot of parallelism at the level of manipulations of the underlying data structure. Okay, so I want to show you the basics for how you'd use a thread abstraction to program parallelism in that case. And of course, our n-body problem is such a case. So let me share the slides and just go over the few of the basic functions and ideas that you'll need. So looking at the slides now, this will be a very high-level overview of POSIX threads. POSIX stands for Portable Operating System Interface, and the idea is that it was an attempt to create a relatively uniform thread interface across a lot of different Unix-type platforms. Okay, so people wouldn't have to learn a new threading model for every hardware, for every operating system that they were using. And pthreads, generally speaking, contain support for creating parallelism, and that's probably the most important part for doing data parallelism that we're doing. So how do you assign a certain piece of the data structure that you're going to perform the operation on to a particular core, where the core is now abstracted to a thread? Synchronizing is still going to be very important. It takes many forms. So it could be one thread cannot do its next operation until it's sure that some other thread has finished its calculation and written its value to memory. It could be that all the threads have to wait until they've all finished before they all embark on some other activity. Okay, it could be, that multiple threads are writing to the same memory location, and you don't want the write to be corrupted, so you have to have some kind of locking when you're doing a shared write to the same location. So synchronization functions are obviously important. There's no explicit support for communication in the sense that the typical threaded model does not have threads passing data back and forth to each other. Usually threads share data because they both read and write from a pool of shared memory. There are some exceptions to that, but threads in that sense are very different from a message passing model, which is a form of distributed memory parallelism, which is actually quite common, particularly in large high-performance computing systems. But threaded parallelism is more appropriate for these relatively low core counts on shared memory machines. And in some ways, you think it's much simpler, but in some ways, what's complicated about it are things that can really get you and that you have to be very careful about. So it's a little harder than it seems. But again, we're using a subset of what I consider multi-threaded programming for multi-core. So the number one function that you have to deal with for what we're going to be doing in class is just the pthread create function. Okay, and what pthread create, as I showed quickly in the synchronous class session, is that you have to pass it a pointer to the pthread that you created. So the idea is that you create a variable type pthread and that you pass it a pointer to that variable, and that always has to be the first argument. Then the second argument is this pointer to some thread attributes, which we're not really going to worry about right now. It lets you set things like minimum stack size and priority. Not important really for what we'll be doing, except in some cases when we're really trying to push the limits of performance. We're okay just using null for the most part, though. The thread function, as I talked about, is going to be a pointer to the function that actually executes the work of the thread. So in this simple model, you're going to send each thread off to some function to do that work. And when it completes that work, then the thread exits. But that could be an arbitrary amount of work. You could have major loops in it. It could be any amount of code. That function, like all function arguments, has a signature that you inherit from the interface, and it is void star return type, void star input. You use those void stars to pass anything into the function that you want and to get anything out of the function that you want. Okay, so when you create the function that you pass in, you also can specify as the last argument here the arguments that will be passed to the function, which are void star, right? So they get passed by a pthreads routine that you don't see, but you specify them as the last argument. And then when the function returns, you return optionally some valid pointer to void, which is data that you'd like to get out of the function. So if that's not clear, it'll be clear when we do a simple example in the next segment. Okay. And then if the operation fails, you get a non-zero error code. You can look up what the different error codes mean. So that's going to be the bulk of what you have to deal with. I'll tell you about a few other functions before I show you some examples. Oh, well, I should say, I did want to show you an example on the slide first. So in this case, we're going to create 16 threads. So you can create 16 variables, or more rationally, you create an array of 16 threads. And then for each of those threads, you're going to call thread create on a pointer to that thread. You're not going to worry about the system parameters. You're going to tell the thread to execute the say hello function, and you're not going to pass in any arguments. So you can just put null here. And so each of those threads at the point it's created is going to start executing this function. This function is prints hello world and returns null, which is a valid return for a void start function. And then the other function, which I'll tell you about in a second, is the pthread join function. So after all these threads are created in this loop, the main thread, which is not one of the 16 spawned to carry out this say hello function, is going to continue, and it would otherwise continue and it would halt until all of the other threads died, but it's a little more responsible and actually necessary when you have more complicated programs to call the join function. So what the join function is going to do is it's going to halt the calling thread on the thread argument right here. So in other words, the main thread will go down here, start executing this loop, and it would say pthread join thread 0, and it won't join it until thread 0 finishes what it's doing. And then it will go back to thread 1 and so forth. So even if thread 5 finishes first, it's still going to block until thread 0 is finished. But since they're all doing the same amount of work, it doesn't really matter for performance. It's all going to wrap up very quickly. Okay, so there's not a lot to doing just the most basic stuff. It gets hard when you have to start reading and writing data to the same memory with the threads, and therefore synchronizing their operations, because it requires you to say when one thread is allowed to continue based on the progress of another thread. And that's where it gets most complicated. But in the simple model we're going to use it, we don't have to worry too much about that. And we compile this with GCC with the -pthread flag. I mentioned a few other functions. I talked about pthread join. The pthread yield function allows you to lower the priority of the particular thread. So the operating system has to schedule the threads. And it's not really that important to use yield if you have one thread per core, because there's nothing to yield to. The hardware is actually designed to make the calculation go faster. But oftentimes, the idea of a thread does not require multiple cores. It's an abstraction. So in a typical multi-threaded program on one core, you might want one thread to be more scheduled more aggressively than another thread in order to make something go faster, be more responsive, and you can use yield for that purpose. Pthread exit will exit a thread and optionally pass the value to an adjoining thread if the adjoining thread exists, and that can be very useful. You can, other useful things that you might run into, you can call pthread self to get a pointer to the thread handle that was used to create the thread. And that's most of it for the simple type of applications that we're going to be doing. And the most important part, and the part that gets most difficult, is to do shared writing. And I showed a simple example here of creating a mutex. And a mutex is created as a variable type pthread mutex t. And the idea is that when you create such a variable, you can call a lock function and pass the lock handle to the lock function and do a write to some memory location. So the idea here is that a particular thread is executing this, when the particular thread obtains the mutex, then no other thread can actually execute any operation that owns the mutex or the lock until this particular thread is complete with the operation that it's using. So the most common way to see it is in a simple form where everyone just tries to obtain the lock to do some kind of shared write. There could be other sections of code which use the same mutex, which are not allowed to continue when the mutex is taken by a different thread. So it can get kind of complicated. But I show an example with the array sum example, the second one that I didn't get a chance to go over in the synchronous lecture. So the amount of functionality we're going to use as pthreads is limited, partly because for a lot of parallel programming, the data parallelism is pretty simple, but moreover because we really want to emphasize using OpenMP, because it's been very successful at a totally different strategy, which I'll show in a second, which is describing the parallelism and allowing the compiler to generate a lot of this code. And OpenMP programming can get pretty sophisticated too. You still have to be very careful about corrupting memory and about race conditions, but you don't have to worry as much about all of the syntax. You're worrying more about how you think about the problem. Okay, but I think it's a very good experience to do it once using pthreads also to compare performance and compare just expressiveness. Okay.